All right, so welcome back. Welcome back to this YouTube channel. In the last video, we have looked at conditional GANs. Yes, we have developed conditional GANs to actually control what the GAN generates. Like the GAN, the basic idea of GAN is to predict a normal image that is indistinguishable for the discriminator. So that is the goal of a GAN based on a uh, data, like based on a data distribution, produce identical data distribution. In the last video, we have learned how to predict, how to control or wait, how to control what the model predicts to actually make it to actually predict one or predict data distribution belong to one class. So we can control how whatever data it predicts. We essentially add another label parameter, and we could just create an embedding. Just like in NLP, we could just create a feature vector representation, and then we could do that. So in this video, we're just going to move on. In this video, we're going to cover a new type of GAN, just like not pretty new. The basic ideas are still there, but we're just going to do some little modifications, some little mathematical, especially loss function modifications and some other modifications to actually build better models, better GANs. Let me just show you some images predicted by Wasserstein GAN versus GAN. I think there should be some images on the internet. Let's see. Yeah. So as you can see here, okay. So these are the outputs. Okay, so I think this is super resolution. I'll just leave it. Just leave it. We'll just move on. I mean, I think I have saw one image in which like Wasserstein GAN perform way better than the normal GAN. I think it is a generation task. So it is a paper, Wasserstein GANs, wrote by I think a researcher. In fact, let's just see what that paper is. I'll just open that paper for you. So this is this. You can just download this paper from here, just from our ARXIV, ARXIV, right? You can just get this paper. It is full of mathematical intuition. You might just go through it. Right. So it is wrote by this gentleman here, right? I hope they all of them are men. Yeah. So these people wrote this paper. So it just like all of you, all everything you see here is just some derivation, and there is one last loss function that they will come to, right? So they'll just come through one last function, which is the only function that we'll be caring about. So first, I have just pasted this code that we have coded in the last video. I just pasted it, and I just made some changes, right, for us to actually build upon. We'll just build upon the previous code, and to actually build Wasserstein GANs, we'll just do some little modification. So right, so the first modification is Wasserstein GAN is actually known for its stability while training. So there will be like less chances of exploding gradient or vanishing gradient. So that is why to actually control the problem of exploding gradient and vanishing gradient, we'll be doing something called gradient clipping, right? So it is a process called gradient clipping, right? So in gradient clipping, what we'll be doing is, let's say if there is a gradient, if there are some weights that are given very much high importance, they're just overrated in your words. Let's say some weights are overrated, some weights are given more or the derivatives are much higher, right? So the change required is much higher. All right, so let's say the derivative is currently something maybe small number, maybe the change is much higher, maybe the model predicts that the derivative should be very much higher, very huge value, and we don't want that, right? We don't want the model to actually bounce off. We don't want the model, for example, when you are predicting a black and white image, or just take a pixel of a black and white image, and you are doing like generating new images. You don't want the model to actually go from black to white directly, right? So you don't want the weight to actually change. You don't want the pixel value to change directly from black to white. because that will cause the model to actually bounce off. First, it goes from white to black, black to white, and it will create instability, right? There will be a huge amount of gradient difference, and we don't want that, right? So therefore, we'll do something called clipping. So we'll just set threshold to the derivatives. So I'll just, rather than having like huge amount of derivative change, we'll just control that. We'll control the derivative values. We'll just clip it, right? We'll just create like a threshold, like, so that's a limit that you can update a gradient, and we'll do, and that is the process of gradient clipping. In Wasserstein GANs, we use this. You can just do this by just creating a class, and then from keras.constraints, you can just import this function or class called constraint, and you can just inherit from that constraint class in the class that we'll be building, clip constraint class, right? That is the first thing that we'll be doing. And then the next thing is we are going to build a Wasserstein loss. So this is actually also a chain that we'll be doing. So in the normal GAN, right? So in the normal GAN, I'm going to uh, tell this concept in a very gentle manner, because I don't want to, like, there is a like whole amount of derivation here in this paper. I don't want to go into that, because like there's a lot of stuff to do, stuff going on here in this paper if you think about it. So I'm going to let me just tell you what is happening here. In the normal GAN, in the normal traditional GAN, we are the discriminator, right, is actually predicting how indistinguishable that the generated image by the generator is compared to the real images that the discriminator is already trained upon. But in Wasserstein loss, the model is actually the discriminator or the critic here. So the discriminator, remember in the Wasserstein GANs, just note that the word discriminator is actually changed to critic, because I am going to come to that point in just a minute. So in Wasserstein loss, the critic is actually forced to predict something called Wasserstein distance. So Wasserstein distance, I'll probably cover that in the one of the next videos, maybe in the math videos that will be coming. That will be coming. I'll try to make some mathematical videos. Deep learning for ML for math for deep learning. Right. So the model actually predict the Wasserstein distance between the true and the prediction. Right. So the critic will actually predict the Wasserstein distance. Right. So that is one. That is another modification that we'll be doing in this Wasserstein GANs. And after that, one more is in the last video, right? So whenever you are building a GAN or GAN, right? Whenever you are building the discriminator of a GAN, the output layer, in the output layer, you'll normally add a sigmoid activation function, because you want the output to actually either be 0 or 1, or any value between 0 or 1. But in Wasserstein GANs, we'll create something called critic, because we'll name the discriminator as critic, because the model will not just predict a value between 0 and 1, but will actually predict just a number, right? It just predict a number that is not, it is not a like a it's not like an option. The model will not actually predict 0 or 1. It will predict something more to actually give some more context and give some more information for generator to actually train better, right? So it will not just give an output, but it'll just give a estimate of how of the Wasserstein distance or the Wasserstein distance between the actual and predicted image by the GAN. So that is the model. So that is why we don't use softmax, or sorry, sigmoid. We'll just clip it like just like that. That is, we are using a linear model, linear layer, right? So it is actually going to be any number of, it can be any number, right? We are not actually using a activation function here. It will be linear. That is out of the infinite values, it can have any value. But of course, we are going to control, it is not going to be a very huge value. And after that, we are another change that we are going to do is we are going to use RMS prop, because the Wasserstein GAN paper recommends us to use RMS prop optimizer with a very small learning rate. So yeah, very small learning rate. And yeah, here what I'm doing is I'll just compile the model with Wasserstein loss. So this loss that I've built here, and the optimizer to be RMS prop. And then we can just build the generator. There is no change in the generator part. So I'm going it just straight up, right. Dense layer, reshape, convolutional transpose, and all that same thing, right? And then here we build the GAN. Here we define the GAN. We add the generator, and we add the critic, and we just right. We'll just get them all together, and then we'll create another function to actually load the real samples from the MNIST data set of that is inside TensorFlow. We can just do that through this function. So we just get this. We just call this function. We just call this object to actually get the training data. And again, we are ignoring the validation data because we don't actually need them. We are not actually solving the problem of image classification. Right. I'm going to yeah, we just do some image speed processing and all that. And then here in this function, I'm going to yeah, I think I'm just going to wait a minute. In samples, I'm going to get a random integer from 0 data set shape and them samples. And yeah, I think I'm just creating x and y's here, right? I'm just okay. I'm shuffling these values. I'm getting these numbers randomly, right? I'm just shuffling these values here, and then here we'll create a function to actually generate latent points, because the input of our generator will be random noise. So to actually generate this random noise, we'll create this function, and we'll reshape it, right? We'll just reshape it to actually be the size, so that we can actually perform the all the operations of the generator. And then we'll create the generate fact samples function, in which we use the generator. We'll take the input as the function. We'll take the function as input. Very sorry, where I am, right? I'm going to use it, call the generator on this random points that are actually generated by this function, right? By this function. And then I have this summarize performance, just to get all the accuracy and save the models, right? Just to save the current model. And I have this plot history to actually plot the history of accuracies. And then we'll finally build the train function, right? In which we'll just create this final training loop, right? We'll just call this function generate real samples, and we'll train we'll update this C model. And one thing I forgot, this one thing is, in Wasserstein GANs, we'll update the gradients of the critic model 5 times or n number of times before updating the generator's weights for one time. So essentially, we'll be updating the critic weights more often than the generator's weight, right? So that is why I have this for loop here, in which I'm going to in the for n critic number of times, I'm going to just update these critic weights. I'm just going to keep on updating these critic weights. For example, for 5 times, I think in the paper they have mentioned 5. Yeah, I think they have maybe 5. Let's see. Yeah, maybe 5. Um, yeah, I mean, like 5 times, I think. Yeah, maybe 5. So they'll update the weights of critic for 5 times, and then after that they'll update the weights of generator for one time, and then again they'll update the weights of the critic for 5 times, and then update the generator for one time, because the Wasserstein GANs mainly depends on the critic, right? It depends on mainly on the critic. The critic will not only give an output 0 or 1, it will provide some more context to the model to actually update its gradients. So yeah, it is definitely useful. And then after that, we'll just run the same lines that we have run. So I'm going to specify the latent dimension, the dimension of the noise vector, which will be the input of the generator. I'm going to call the define generator, and then input the latent dimension, the dimension of this input noise vector. I'm going to define the GAN. I'm going to put in the generator critic. We're going to load some real samples, and then we could just train it. We could just I will just call this function. with these inputs, again, I'm not going to run it. I have run it for some time, but it took a lot of time. Yeah, it, I mean, like, I have tried, but it definitely does take a lot of time. And because I'm also recording, my computer is getting a little slow. So yeah, that's it for this video. And I think I'll see you in the next video. So